Right. Hello, everybody. Welcome to Zombie Math. We'll be applying ordinary differential equations and 2D molecular dynamics to simulate a zombie apocalypse. If you've seen this before, it's because I recently presented this at our school's math symposium. Super exciting. Really happy to have had that opportunity. Um, After presenting, I was just like, I want to share this with the rest of the world. So let's get started. My name is Abdou, and I'm the head of the zombie research for today. All right, so first of all, special thanks to Dr. Ornella Mate. This model and presentation would not have been possible without her. I really appreciate all her help. Let's get into it. So here's our overview for today. First, I'll tell you guys what zombie math even is, introduce the SIR model, introduce our zombie model, do a bit of analysis of our model, and then apply molecular dynamics in the 1D and 2D case. So, what is zombie math? Well, it's just for now, it's the culmination of my work in my senior project class thus far, the first half of it. I'll be teaching you guys how to build your own epidemic model, and my future goals are to apply this to a video game of some sort. Still figuring that part out. Um, I'm very open to ideas, like what kind of game it should be applied to, whether or not it's even, you know, optimal to apply this form of math to video games or like, this sort of problem. But I'll show you guys what I've come up with. Hopefully, you guys think it's really cool because I think it's pretty cool. Okay, so first off, what is the SIR or SIR model? It's the fundamental framework that we have to predict how a virus or disease is going to spread throughout a fixed population, right? Um, let's see how that's set up. So you have three groups in the standard SIR model. You have susceptible, infected, and recovered, right? So susceptible individuals are individuals who, again, are susceptible to the virus, right? They're able to be infected. As for the infected group, these are people who have been infected by the virus and are able to transmit the virus to another susceptible individual. For our recovered group, these are individuals who have previously had the virus and have now recovered from the virus and no longer need to worry about being reinfected, right? They have some immunity uh, in the standard SIR model. I need to make that very clear. And when you add up the total population in these three groups, you get N, which is just our total population. So you might be wondering, where do ordinary differential equations come into play? Well, we have our system of ordinary differential equations here, right? We have our dSdt, didt, drdt. And what this allows us to model is the rate of change for the population of each group in time, right? Over time. And we can see how the groups transition from susceptible, or how individuals transition from susceptible to infected to recovered. So let's start off, right? We see minus terms, we see coefficients, we see all these, like we see S and R, but what does it really mean? So a good rule of thumb when you're working with a closed system like this, a closed system of equations, is everywhere you see a negative coefficient, there will be a positive coefficient um, of that same term added somewhere else in one of the other equations, right? So here, if we look at our first equation, ds dt, we have negative beta s times I, right? And what that is that allows us to simulate mathematically. This okay. Sorry. This is mathematically, this is how we show interaction, right? So this is our interaction term. For our case, working with zombies, you can think of this as a bite, right? So the susceptible individual is being bitten by the infected individual. You can think of it that way, right? Um, and you notice it has a negative coefficient, uh, and B, or not B, but beta being our infection rate. Um, that turns our susceptible individual into an infected individual. So we have to account for that in our infected equation by adding that term or that individual, right? And as for the infected individuals, naturally over time, they'll recover from the viral infection or virus or whatever disease, whatever you want to call it. And they get removed from the infected group and go to the recovered group, right? Um, so the growth of the infected, right? The growth of the infected population is completely dependent on the susceptible group, and the recovered group is solely relies on the infected group for its growth, right? Um, so alpha being our recovery rate, slowly over time, as you'll see numerically in this next slide, over time, infected recover, and then boom, right? So what are you looking at here? This is our numerical solution for the standard SIR model. Uh, we use Euler's method in MATLAB to get these graphs. Um, at the in the x-axis, we have our time in days, right? Uh, and in our y-axis, we have our population. So you can see in blue the susceptible, uh, due to a really high infection rate, right? A really high beta coefficient. Their population just tanks, right? They instantly, like, I wouldn't say instantly, but very rapidly enter the infected group. So that's why you can see the red line, the infected group, kind of skyrocket, and then with a fairly normal or lower recovery rate, you can see over time the individuals in the red group enter that green group, which is the recovered individuals. Hopefully, this color coding is helping. Let me know if you have a better way to set this up. So, now that we have a fairly good idea of what the standard SIR model is, we'll be using that in order to build our own model up piece by piece, right? We'll be adding more groups, we'll be adding more coefficients. Uh, we'll just try to make it a lot more complex than before. So, let's get into it. I drew this to kind of show you guys the flow or balance of the populations in each group, how things move around. Um, and I can explain that for you guys now. If you guys would like to look at the S group in blue, the darker blue here, right? These are our susceptible individuals. So from the susceptible group, they can either decide to quarantine, which is our Q group in purple, or they can be exposed through some individual and end up in the exposed group, right? So from quarantine, let's assume I'm some person who's seeing a bunch of chaos outside, right? I don't want to go out there. I'm going to go lock myself in my room. That's what this quarantine group is. People who isolate from the entire system, stay in their room, but eventually you're going to run out of food, you're going to run out of water. All these things become modeling assumptions. So we assume that after some uh we assume that people over time will leave the quarantine group by some coefficient rho up here, uh, or they enter the quarantine group through some coefficient lambda here at some lambda rate, right? Um, Back to the exposed group. How does one get exposed? As we mentioned before, uh, an infected individual has to basically expose a susceptible individual to the virus. So what we do here is we have three groups that have that ability to transmit the virus, that being the infectious group. This is different from infected, right? They're still technically infected by the virus, but here we're explicitly stating that they're just infectious. These people are still human, right? Exposed individuals are still human. They may have a bite, but they're still human. Infectious individuals, still human, but they may be pretty sickly right now, right? Um, so the infectious individuals are able to uh, infect other susceptible individuals. The slow zombies, denoted ZS here, are able to infect susceptible individuals. And the fast zombies, denoted ZF here, are in pink, are able to infect susceptible individuals. That's why we have three different beta coefficients here with different rates, depending on whatever modeling assumptions you have, that can infect or bite. For the infectious, I like to think of it as like coughing in their face, right? But like bite or cough, right, and infect a susceptible individual. That's how they end up in the exposed group. One thing about the infectious group that I find interesting is that they can either become zombies or they can recover, right? Let's say I'm pretty ill from the zombie virus that's been developing in my system for a while, right? But I start getting better. I start recovering. Those individuals that enter the recovered group here in green, um, for a time they have some immunity, but after a while, since we want to kind of show some more interesting behavior, I like to allow this recovered group to become susceptible again. So they lose their immunity at some rate mu. Um, Again, back to the infectious, they're able to become slow zombies or fast zombies at a 50% rate, right? Like whether if they become a zombie, they either have a 50% chance of becoming a slow zombie or a fast zombie. And of all the zombies, depending on uh, who they run into, they may be killed. That's another modeling assumption that I just want to have fun with. Like, what if the humans could fight back? Uh, this is this is really like modeling it in like hand to hand combat. But let's say KIS through K4S, right, for the slow zombies. What that's saying is the KIS um, constant, right, has a higher chance. It gives the zombies or the humans, right, the healthiest humans. So this is ranking from most healthy to least healthy, depending on whether they're susceptible, completely unharmed, exposed, maybe they got bitten, infectious, maybe they're like barely able to stand, and then recovered, who are kind of like slowly getting their health back a bit, right? So this ranges in probability for the those humans, depending on which humans the zombies run into. They may be killed at a different rate, right? Um, Same with the fast zombies. Uh, how I like to think of it is the fast zombies are a lot harder to kill than the slow zombies. So uh, the kill rates for the slow zombies has to always be higher than the kill rate for the fast zombies. Hopefully that makes some sense. Um, but whenever they're killed, they enter this group here called the dead group, which is just all the dead zombies. This does not include dead humans, right? We assume there's no birth or death processes. This is just a new group for zombies who are incapacitated completely, right? So that already was pretty complicated, but if you were able to follow along, great job. What we have here is the system of differential equations for all of those groups. You saw with the SIR model earlier, right here, we had 3 groups. Now we have 8, so we need 8 different equations, right? To tell what's going on here, let's use one of these equations as an example. They all follow pretty much the same logic, right? We have the exposed group here, the exposed ODE, and at a rate of beta s, right? Beta s corresponding to the slow zombies times susceptible times the slow zombies, right? And then the fast zombies, and then the infectious humans. You can see these are added. These are now added to the exposed group, because it's a susceptible becoming exposed now, at these rates. And then we have this sigma e term here, which is just the incubation rate, which is the exposed group eventually becoming infectious, right? The disease virus has progressed enough for them to be able to infect other individuals. So everywhere you see a positive coefficient here, there is going to be a negative coefficient somewhere else. So you can see that these specific terms were taken out of the susceptible group, and this sigma e term that's taken out of the exposed group ends up in the infectious group. So that's pretty much how the math works for that. It's not super hard to set up. If you can come up with your own groups, come up with your own rates, you can model some sort of epidemic and see how it flows, right? So here's the numerical solution for that system of equations that I just showed you. We start off initially, like our initial conditions, we start off with 1 fast zombie, 1 slow zombie, and make the rest of the group susceptible, right? Individuals. So as you can see, same behavior with the susceptible individuals. Their population just kind of tanks because now they're being filtered through the other groups. We have in purple here the quarantine group. Some humans decide to quarantine. A lot of them decide to quarantine at the beginning, but slowly they start leaving, right? They have to leave their homes. You can see a group of people are getting exposed at some time. And then those exposed people eventually become susceptible, infectious, right? And of those infectious individuals, a lot of them recover, or a lot of them turn into zombies. Here in cyan, we have the slow zombies, and here we have the fast zombies in pink, right? And these zombies tend to persist for quite a while. And this red line here is the dead zombies. So when those zombies are being killed by the humans, the population of the dead zombies kind of just continues to increase. So what we have with our end behavior here, after let's say 10,000 time steps, is you'll have all dead zombies, all and the rest you'll have like some slow or fast zombies, because there'll be no more humans to infect and no more humans left to kill the zombies. So that's when it becomes a little stagnant, right? So what does military intervention look like? This is a fun one. So we model military intervention as a Gaussian. You can see that we multiply that Gaussian by the group, right? In this case, it's slow zombies. In this case, it's fast zombies. And we're assuming that this event, right? Military intervention. Imagine it's a nuke. Imagine it's a nuke. We're assuming that this military intervention is only targeting the zombies for now. You'll see some behavior that is a consequence of that assumption. But once those zombies are dead, they're subtracted from their respective groups, slow zombies and fast zombies, and then they're added to the total dead zombie equation, right? Because you need that negative coefficient, or like the opposite sign somewhere else in the system because it's a closed system. So here's what it looks like once we add military intervention, right? Again, we start with 1 fast zombie, we start with 1 slow zombie, and then we make the rest susceptible. So Same behavior as before, but now at the like when the nuke drops, all those zombies in the cyan and pink group, boom, skadoosh, they're dead, right? A lot of them die. But it doesn't mean that the entire system is dead, right? This gives the recovered a chance to enter the susceptible group again, and then you can see again the cycle continues. And because we didn't target any of the infectious individuals, right? Because we're assuming that the military still has some heart. They don't want to target humans. They only want to target the zombies. The infectious humans are able to reinfect the population again. So the zombies are able to make a comeback, and then you'll see similar end behavior to uh, the original numerical solution. So let's look at some cases, right? What does it look like when there's rapid zombification? Uh, if the if the zombie infection rate is so high that basically or essentially the entire system becomes zombies before the anti-zombie event, before the nuke gets dropped, boom, they're dead. Pretty much the entire system is dead. I was having fun with this. I'm sure you guys could have some fun with this, but that's what it looks like, right? And then in this case, we're not assuming that the rapid zombification rate is super large anymore. Instead, we're going to assume that the military is intervening for quite a while. And it's easiest to see on the graph on the right, where we have 10,000 days instead of just 1,000. You can see that the Gaussian is affecting, or the military intervention is affecting the zombie population, keeping the cyan and pink lines at 0 for a very long time. As soon as a zombie pops up, they're dead, right? That's how you can kind of think about it, or kind of, yeah. But as soon as that military intervention is over, the zombie populations are able to make a comeback again, because as stated previously, we did not target the infectious group, right? These are the people that are still human, and they're infecting other humans again. So that's pretty cool. We have our graphs. We have the ability to track how each group changes over time. But in the form it's in right now doesn't really help me, right? My goal is to try to apply this to a video game at some point, maybe whether it's a zombie game, whether it's some other resource gathering, research controlling game, doesn't matter, right? The point is the SIR model is really good at tracking the groups over time, but it's really bad at tracking the individuals over time, right? So that's where molecular dynamics comes in. So, what is molecular dynamics? Well, what molecular dynamics does is it allows us to track the motion of a particle I in, you know, within a population of n particles, right? Um, if we assume that xi is the position of that particle I, then we can assign a velocity, right, dxi dt, to that particle, or we can assign an acceleration, which is the second derivative of xi in time, to that particle. So doing that, this is how we'll define our motion in one dimension, right? This isn't even the final formula that I actually use, but this is simplified for ease of understanding. The key point or the key idea of these equations is that there's an attraction repulsion relationship between susceptible and individual or infected individuals, right? So for susceptible, if I'm a susceptible individual, right, I don't want to get bitten by a zombie. So you know what I'm going to do? I'm going to run. I'm going to run away. It's that simple. I don't want any part of that. If I'm an infected individual, right? In this case, we're going back to the classical SIR model, but you can still kind of think of this as your zombie, right? If I'm a zombie, I'm hunting them down. I'm chasing them. And that's my only goal. That's my only goal, right? So, the closer I am to an infected individual, the faster I'm going to move. Or yeah, if I'm susceptible, the closer I am to an infected individual, the faster I'm going to run away. If I'm an infected individual, the closer I am to a susceptible individual, the faster I'm going to run towards them, right? I really want to chase them. And for this scenario, we'll assume that they recovered, they're not afraid of getting infected again, and they have no reason to chase the susceptible individuals. So they stand still for our purposes, right? So this is what it looks like um, in one dimensions, right? We do have boundary conditions, but that's not that important at the moment, right? This is just a showcase. So you can see our infected individual in red chasing our susceptible individuals to the left. And you can see, right? Recovered, they're not moving. Susceptible, they want to skedaddle out of there. But they run into a wall, right? They run into the bounds and then eventually get caught. So that's what just the motion looks like. That's just how we define motion. But how do we define the collisions? Like, what are the collisions? What do they represent in our model? So, this same group collisions, right? Let's say I'm an infected, you're an infected, right? We can't overlap. We don't want to overlap, right? Like, physically, that's not possible. So, all this first equation is saying is that me, a susceptible, you know, getting very, very close to you, another susceptible, I'll just stop, right? So at the next time step, I retain the same position I had at the previous time step, right? And same for infected. If you're infected and I'm infected, uh, the if I get too close to you, I'll just stop and then have that same position, right? Uh, so that's for same group, but how do we define the you know collision between susceptible and infected? uh, this second equation here, what it's saying is if you're an infected individual and I'm a susceptible individual, and you get really, really close to me, I'm now an infected individual. We're now a family, right? That's all it's saying. And this can be any infected individual getting too close to a susceptible individual. Um, they turn that susceptible individual into an infected, right? That collision is modeling our interaction. And as for turning from infected to recovered, we have that covered as well. Um, okay, so for we define some recovery time, right? Where we assume that once this recovery time has lapsed, right? The infected just naturally turns into a recovered individual. They just naturally become recovered, right? So here's what it looks like all together. You have your infected getting faster the closer they get to a susceptible individual, uh, in blue, right? And that susceptible individual, once there's been that collision, turns into an infected individual, and then they all chase the susceptible individual on the right. But before they can reach it, they recover and turn green and stop moving, right? Um, very clean, very simple. Remember, this is for just 3 groups. When it's 8, it'll get pretty messy, but that's for future me to handle, right? Uh, how do we turn this model from one-dimensional to two-dimensional, right? Um, we're sticking again with the standard SIR model. This is actually a modified equation for motion. That right? This is my finalized equation for motion. I actually have a plus epsilon in the denominator on the right just to cover the cases where susceptible are equidistant from the infected, they won't just get stuck, taking that average. But what you notice here in the 2D case is that our xi is now a vector of two components, vertical and horizontal. And on the right, we're actually going to be taking the norm of the distance between, you know, susceptible and infected. The recovered the recovered equation stays, pretty much the same, but all the key ideas are the exact same for 2D as they were in 1D. So we can get straight into showing you guys some scenarios, uh, and let me know what you think. All right, so first here we've started with 4 infected, 4 susceptible, and 2 recovered. Uh, you may be watching this and asking, where's the other susceptible? Like, I don't see it. Neither do I. Um, However, when like screen recording or outputting or exporting kind of like animations in MATLAB, the frames, if you don't capture enough frames, some parts may be missing. But yes, the initial conditions I did start with 4 of infected and susceptible, but the since the positions are randomized, that susceptible just got turned into an infected way too quickly. So now they're going to hunt down the rest of the susceptible as a red infected. And then in this scenario here, I just have more susceptible than infected. I added a ton more susceptible. As you can see, now that there's a lot more susceptible, the infected move a lot faster. Uh, the susceptible will continue running towards the corners because that's the furthest position away from all of the infected individuals, right? That's as far as they can go. And if they don't reach you'll see in this next scenario where if the infected don't reach the susceptible in time, um, they'll just recover before then, right? So we have our 4 susceptible in blue running towards the corners, and then like maybe one gets turned into an infected, right? That one, I think it's like around here somewhere, gets turned into an infected, and then they chase the rest of the susceptible. But I think it's just really cool to see like the actual dynamics, right? Seeing everything move. This started off as just like 3 equations a couple months ago, and now you can visually see, um, you can almost see the zombies kind of like thinking, like deciding which way they have to go to get to like their nearest prey, and I think that's like super cool. So in this next scenario, I wanted to have a little bit of fun, right? So I had 1 infected versus 150 susceptible, and you can see it's very chaotic, right? All of those, because there's so many susceptible individuals, the infected can rapidly like reproduce, right? And then they just quickly catch up to the rest of them. Like there's so many, and they get caught so quickly that it looks like they're just like super close together. Uh, but some of them, like while chasing the last susceptible, which is in the corner, it's a little bit cut off in this GIF, but it's in that corner. Eventually, they recover before they can reach it. Um, I think it's just super cool seeing all this motion happening. Let me know what you guys think. Let me know if there are more scenarios you'd like to see. Um, but without, you know, otherwise, this leads into my conclusion where we've applied 2D molecular dynamics to the classical SIR model. You guys now have the tools to create your own equations for the epidemic model. Um, the MATLAB code, that's all you. That's all you. I'm so sorry, but that's all you. Um, and hopefully, the next time you guys see an update on this model, I've extended it to the full model, right? The full zombie model, the system of 8 equations that I showed you guys earlier. For that, I'll have to define a lot of um, conditions, right? Like, for example, the quarantine group, if they're in this enclosed space, where do they go? Could probably just make them work the same as recovered currently does, but you get the point, right? I have to figure out, okay, all these groups, what are their reasons for moving? And that again is a problem for future me. Uh, First of all, thank you guys so much for sticking around for so long. I know this is a long video, but I was really excited to get this out. Just talk about this model, have it recorded while it's like fresh on my mind. Um, and this will allow you guys to just see the evolution of this model for the future. Thank you again. I hope you guys have a good day. Follow if you'd like to see more cool stuff. Bye bye.